Hello and welcome to this 5-minute short. This 5-minute short is looking at how we model control valves in ADRIAN where we've got choked flow through the control valve. So where we're going to start with this is Capri. We've got this sheet here, which is actually from if I go to Capri, it's from the required relief rate, control valve vapor. And we've pulled that in, and we're going to use that to estimate the flow through our control valve, so then we can then model it within ADRIAN. So I've just picked a fluid carbon dioxide. We're at 20 bar gauge, so 21 bar absolute, 15 degrees C. I've created an estimate of a valve, so I've got a CV of 10, and I've got a nominal size of 26.6 mil, a 1-inch line. These values here come from this sheet here. So again, just to show where that is, you've got this table D2. This is table D2, and I've assumed this is a globe single port 3V port plug valve for the purposes of this exercise. So that's pulled those through, again 1-inch lines either way, and what it comes down to is with that 20 bar gauge upstream going to atmosphere, I've got a flow rate of 4,829 kilograms an hour. So that's how much flow I'm expecting to get through my valve. I then need to think about how I'm going to model that in ADRIAN. So if I open up an ADRIAN model, and you'll see that there's two here. There's this choked valve model and a control valve K value model. There'll be another 5-minute short explaining what's going on with this one. But let's look at this model here first. So I just double click in here, my upstream node, and I've done it as a node, not as an upstream vessel, because I don't want inlet losses. I want to try and model this as best I can as an upstream pressure and a downstream pressure and flow through the valve. So I've deliberately done it as a node. It's not a stagnant vessel. Defined it by pressure, 20 bar gauge. This is the parameters for carbon dioxide. So we've got that in there. Going to atmosphere to ensure I get choked flow. I've got my 1-inch pipes, and I've done 0 length, because I don't want any pressure loss in the pipe work. I'm literally modeling what's going across that valve. And the way we've modeled that valve, if I click in here, is the diameter is the pipe diameter, so it's a fitting from over here. So that will be picked up in the line size. But then we need to work out this minimum flow diameter here. And then you see in this case, I've got 16.1, which you may wonder where on earth that's come from. But that minimum flow diameter, that's what's going to drive a choke or not a choke. So that's a local flow minimum. If we're going to have choking, that's what's going to define the flow through that choke, or partly through that choke. Then you see the K value is 0 when I've got my choking condition. So where does 16.1 appear? I then go back to my sheet here. And if I scroll down, there's a little correlation that you can find. And I did look, it was a definitive reference. It seems to be more of a rule of thumb. But that area, that effective area in your control valve, can be approximated by the CV divided by 29. So what that's then done is it's told me that the area, effective area of that control valve is mimicked by a 0.345 square inch orifice. You can convert that into a diameter, which you can see there is 16.8. Not quite the same value, but 16.8 is my starting point. So I then went back into ADRIAN, and what I did then was I initially put 16.8 in here, ran the model, and then iterated it a bit to get to a decent value. So if I press calculate again, we can see this is pipe 1, so node 3 to exit 1. And what we're looking for is changing that little value inside to get close to my flow. And you can, how much time you want to spend to get as close, but 4853, I've got 4829. Purpose of this little video, I'm happy with that. And what I've got then is a little model that I can use within ADRIAN to mimic that control valve in a choking position. And then the next video we're going to look at is how we do that for the non-choking condition, and then we'll see how we wrap it all up into an ADRIAN model. Thank you very much.